Right, so metallic bonding, usually the third of the bonding types that we cover, but actually bizarrely very frequently asked on IGCSE specifications, and it occurs obviously in metal. So if you have your periodic table in front of you, it occurs in elements that are on the left hand side and the middle of the periodic table. So let's take for example sodium, which is in group 1 of the periodic table. Just find it on your table now. And sodium is in group 1, which means, well, the group number means it only has 1 electron in its outer shell. And that outer electron becomes delocalized. In other words, if you have a row of sodium atoms lined up next to each other, here, their outer electron leaves it and is able to wander, if you like, through the structure. This means the atoms are no longer atoms because they've effectively lost an electron. So they become ions, or in this case cations, because they're positive. So here we have the structure of sodium. So we have rows of these positive ions lined up, surrounded by a sea of delocalized electrons. And that is in fact the definition of metallic bonding. It's a giant structure of positive ions, that's shorthand for positive, surrounded by a sea of delocalized electrons. So delocalized means that that outer electron no longer belongs to its atom. Okay, it's floated off, it's delocalized, so the atom then becomes an ion. So a giant structure of positive ions surrounded by a sea of delocalized electrons. And the attraction between the ion and the sea of electrons is strong, which means metals have a high melting point. So strong attraction between the positive ion and sea of delocalized electrons. Now, do you think the strength of the metallic bond varies from metal to metal? That's a question you should be asking yourself. Well, what might affect the strength of the attraction between the positive ion and the electrons? Well, if instead of it being a 1+ ion, it was a 2+ ion, there would clearly be a stronger attraction. So, are there a particular type of metal on the periodic table that would form 2+ ions? And the answer to that question is yes. Magnesium, for example, would form a 2+ ion. Calcium would form a 2+ ion. So metals within group 2 have stronger metallic bonds than metals in group 1, because we've got 2+ ions and 2 delocalized electrons from their outer shell. Now that first point, I must admit, is one that isn't often asked in exams. The next point is, why are metals ductile and why are they malleable? So first of all, we obviously have to decide what these words mean. Well, ductile means that if you pull on a material, it can be drawn out into a wire. So think of grabbing each end of a piece of metal and pulling as hard as you possibly can on it. Clearly you can't, but if you were incredibly strong, the metal would stretch and stretch and stretch and stretch and stretch into a wire. Malleable means that you can hammer it into shape. And the reason that metals do these two properties is exactly the same. The reason for that is you have layers of ions. So imagine if we try and hold this end and pull this end of the metal away from each other. What actually happens is by pulling on this end, you actually pull the ions over each other. And the fact that the ions are in nice, orderly, regular rows means that the ions, when force is applied to either end, can slide over each other. So rather than the structure falling apart, the ions just slip and slide over each other, and so rather than it being in a large lump, maybe that you started with, it gets drawn out and drawn out and drawn out into a wire. The same thing happens if you hammer it. If you hammer on this layer of ions here, you whack it with a hammer, okay, all that happens is these ions slide over and move down. Okay, the structure actually remains intact, so the metal doesn't shatter, it just changes shape. So what the examiners are looking for is, why is a metal ductile or malleable? Because you have layers of ions, and that's the first mark. And the second mark that they're looking for is that can slide over each other when force is applied. So that is a very, very popular exam question. And the third point on this page is also very popular. Why can metals conduct electricity? Those of you with a reasonable knowledge of physics will clearly point immediately to the sea of electrons. Okay, so the reason they conduct electricity is that the delocalized electrons are free to move. And as they're free to move, when a current is, well, when we try and pass a current through it, the electrons can move through and thus conduct the current. So why can they conduct electricity? Metals have delocalized electrons which are free to move and carry, oh, I've written R, and carry the charge. So to be honest with you, the final 2 points are the most important points here. This is where the exam questions come. Quite often they give you a diagram of the metal and they say explain why such a metal is ductile or malleable, and then explain why it can conduct electricity. So you need to know those, and that would, a question like that would be worth 4 marks, 2 points for each. The only other point I wanted to make about metallic bonding was about alloys. Now an alloy is a mixture of 2 different metals. So instead of having your nice metallic structure like this of regular identical ions, you might replace some of the ions with ones of a different size. So let's replace this one here with a much bigger ion. Okay, and maybe let's replace this one here with a much bigger ion. How do you think this would affect the properties of the alloy? Well, in theory, we should still be able to conduct electricity because we've still got a sea of delocalized electrons running through the alloy. But what we no longer have are rows of identical ions. The rows and their regularity have been interrupted by these different metal particles or different metal ions placed in there. So this means the layers are no longer able to slip and slide over each other, and therefore the metal is no longer ductile or malleable. So yes, there is a change in properties. Okay, the alloy is not malleable as there are no layers which can slip and slide over each other. Now, I've seen that asked on an IGCSE paper, but the real focus should be back on these 2 points here. Why ductile and malleable? Why can it conduct electricity? And that's the end of this video.